Okay, now let's talk about the derivative rule for logarithmic functions. A logarithmic function is pretty easy to identify because you're going to see an log log or a natural log somewhere in the function rule. Exponential functions and power functions were a little bit more subtle. You had to really think about where the input was going to be able to distinguish whether it was a power function and would follow the power derivative rule or an exponential function that follows the exponential derivative rule. But log functions, you know it's a log function. And the way you know it's a log function is that the input is being sent to the log. You're taking the log of something that involves the input. And that something is called the argument. I'm going to refer to that as the argument. That argument can be a plain X. That argument can be like a binomial or some other expression that involves the X. But somehow that input is getting sent to some expression and you're taking the log of that expression. And a quick reminder, logs have a constant base. It can be log base 5, log base 3. If there's no base indicated in that subscript, it's understood to be a base 10. Again, if you need to dust cobwebs off of logs, go back to the first page of these notes and rewatch those videos that review log rules and how to read log notation. We're going to go to the calculus. So how do I find the derivative of a log function? Again, there is a generic rule. This is the only one you need to memorize. And then there's a special case. We'll talk about both of these, but we'll start with the generic one, because if you know the generic log rule, you're going to be able to derive the special case. So what does this rule say? Oh my goodness. It says, to find the derivative of a log function, we start by doing 1 over the natural log of whatever that constant base was. So that's the first piece of the derivative. Then we multiply by 1 over g of x. That was your argument. 1 over the argument. Okay, and now here comes the chain rule part. So in the power rule, the input was sent to the base, so we tacked on the derivative of the base. In the exponential rule, the input was sent to the exponent, so we tacked on the derivative of the exponent. In the log rule, the input is being sent to the argument, so the chain rule is going to tack on the derivative of the argument. Okay, well, let's just look at an example before we even think about this special case. And I'm going to work this example 2 ways. Oops. I'm going to use the function as it's written, and then I'm going to use an algebra rule because it's a good review. You'll need to know this rule later. Okay, number 3. This is a logarithmic function. It's actually written as an equation, but if I wanted to, I could write that in function notation, and I could see that the input x is being sent to this argument. My argument is actually x to the 5th. That 5 is directly touching the x. So that is my argument, but those parentheses are understood there. And this log function has a base 4. Okay, and I rewrote my generic log rule over here just for reference so I could zoom in. So let's follow the rule. If I wanted to find the derivative, and we're using the dy over dx notation for derivative instead of y prime, but this is basically just y prime. Okay, so what does my rule say? Oh my goodness. Okay, let's look. The first piece right here, what is the first piece saying? It's saying we take 1 over the natural log of the base. Whatever that base was, 1 over natural log of the base. Well, my base was a 4, so I'm going to do 1 over natural log of 4. Okay. Then the next piece, that says I'm going to do 1 over whatever the argument was. Whatever that argument was. In this case, my argument was an x to the 5th power. I'm going to multiply by 1 over the argument, exactly like I see it, x to the 5th power. So I have 1 over the natural log of the base. I have 1 over the argument. And now here comes the chain rule. Okay, chain rule. for this last piece, I'm taking the derivative of the argument. The input was sent to the argument. So my chain rule is going to tack on the derivative of the argument, which was x to the fifth. So let's clean this up. So that would give me 1 over natural log of 4. Again, you can find natural log of 4 on your calculator. It's going to be some decimal number that doesn't terminate or repeat. So we just leave it natural log of 4. And then I have 1 over my argument. And then the derivative of x to the fifth is just power rule, right? That's just going to be 5. I drop my exponent down to the front. Rewrite my base. So that's an x. And then I decrease the exponent by 1. That drops my exponent to a 4. And technically I tack on the derivative of that base. But that's just 1, so we don't really need to write that. Okay, so the derivative of my argument is 5x to the fourth. So now let's clean that up. When I clean this up, I can put that 5x to the fourth over a 1. And then when I go through and multiply all my numerators together, that's just going to give me 5x to the fourth. And then I go and I multiply all my denominators together. That's just going to give me natural log of 4 times x to the fifth. And then I can simplify this. These x's right here will divide out. I'll have 1 factor of x remaining in the denominator. And since order doesn't matter when we're multiplying, we can flip-flop that order just for clarity. We don't want that ln of 4 times x to accidentally look like an ln of 4x or something. So we can move that factor of x in front of the ln to make it really clear it's multiplying. So my derivative is just 5x natural log of 4. Okay, now I'm going to show you how to get this exact same answer a slightly different way. But if you know this way, this way gets you the answer. Here's my answer. But if you know some algebra, it might make this slightly easier. So let me just show you how to get the same answer with a little algebra trick. Okay, we're going to use a log rule from algebra to rewrite the equation. I'm only doing algebra, so I'm going to leave this y equals. No calculus is happening here. My log rule says if you're taking the log or the natural log of an argument that has an exponent, and this one does, my argument is x to the fifth. It has an exponent of 5. I can rewrite this by dropping that exponent in front of the log. So I really have 5 log base 4 of x. And the reason why this is helpful to me is now my argument is just a plain old x. So later, when I go do this chain rule, I'm just tacking on the derivative of x, which is 1. So let's see what that looks like. So let's find our derivative now. Okay, so the derivative says, well, one little clarification really quick on this derivative. See how there's this 5 out to the front? Technically, that 5 is just going to show up in our answer. It's along for the ride because technically there was an understood 1 in front of that log in the rule. And so there's an understood 1 in our answer down there. So I could really rewrite this rule. If there was a 5 in front of that log, then I would end up with a 5 in my answer. Really, if any constant number in front of that log is going to end up in my problem. So that 5 is just there. Later we'll learn something called the product rule and we can prove that. But right now the 5 is just there. So what does my rule say? Then I'm going to do 1 over natural log of the base. So I'm going to multiply by 1 over natural log of the base, which is 4. Okay, so natural log of 4 times 1 over the argument. And my argument now, y'all, is just plain x. So I'm taking the argument of a plain x. And now when I tack on my chain rule, I'm just taking the derivative of the argument, which was a plain x. And like I said, the derivative of a plain variable is just 1. So when I go to rewrite this, I really have 5 times the 1 over the natural log of 4 times 1 over x times the derivative of x is just 1. So I don't have to write that. And now when I go to clean all this up, I can put that 5 over a 1. When I go to multiply, all the numerators together, that's just a 5. When I go to multiply all the denominators together, that's just an x times natural log of 4. So we end up with the same answer, but it's just a little bit prettier when your argument is a plain old x, because it makes your chain rule way easier. You're taking the derivative of a plain old x. So this simplifies it a little, but was it necessary? No. Can you use just your function as it was written? Yes. You can get the same answer. So practice it both ways. See which one you like better. Okay, so now let's look at one of those special case scenarios. What is going on there? Okay, so we have a function that is a natural log. So this function is a natural log. From algebra, you should know that a natural log has an understood base of e. So natural log of x is the same as log base e of x. So I could rewrite this as log base e of x to the 4th. And that is my argument right there. I'm going to work this problem 2 ways like I did the previous one, but we're going to work with the function as is. So I'm going to use my generic rule and then explain where this special case rule came from. But if I rewrite it with log base e, I can use my generic rule. So let's do it. Okay, so then my derivative would be what? So the first piece is 1 over the natural log of the base, which is an e, times 1 over the argument, which is x to the 4th, times, here comes the chain rule, the derivative of the argument. So I really have the derivative of f is equal to 1 over 1. The natural log of e, you know that from algebra, that's just 1, times 1 over x to the 4th, times the derivative of the argument. That just involves power rule. That's 4x cubed. So when we put all that together, I can write that 4x cubed over 1. So I multiply all my numerators together. That's just 4x cubed. I multiply all my denominators together. That's just x to the 4th. And then when I simplify, I'll have 1 factor of x remaining in the denominator. So the derivative of the original function is 4 over x. And I'm going to show you how to do that by using the log rule that'll drop the exponent down in front of the natural log from the beginning and make this a lot easier to understand. Oh, but before I do that, let's talk about why this was a special case. When we compare these two derivative rules, they both have 1 over the argument. They both tack on the chain rule, which is the derivative of the argument. The only thing missing is this 1 over natural log of the base. And that's because if your base is an e, 1 over natural log of e is just 1 over 1, which is 1. So you don't really need to put it there. So if you recognize that, it just simplifies the rules a little bit, but you don't need to know that. The generic rule will lead you to that answer. You just need to know that the natural log of e is 1. Okay, now let's do the algebra equivalent method and get this same final derivative. Okay, my rule from algebra says I can rewrite this function, no calculus happening, so I'm going to leave my f of x notation, by dropping the exponent in front of the log. If you're taking the log or natural log of an argument with an exponent, you can drop the exponent down. So I really have 4 natural log of x. Okay, well that 4 is along for the ride, so when I go to do my derivative, I'm going to have the 4 there. And now I'm going to use my derivative rule for natural log of x. Okay, I'm going to use my generic rule. So the first piece says I need to do 1 over natural log of the base, which is e. But that's just 1 over 1. Times the second part of the rule, this part right here, it says I need to do 1 over the argument. My argument now is just a plain old x, so I'm just doing 1 over x. That's nice. Times the chain rule part. The chain rule says tack on the derivative of the argument. But again, my argument's just a plain x now, and we know the derivative of x is just 1. So again, that's just 1. So I really just have 4 times 1, those are side by side multiplying, times 1 over x times 1 again. That's just a 4 in the numerator and an x in the denominator. That is the same answer as we got before. The